I'm Simone Montangero. I'm the director of the Quantum Computer and Simulation Center of Padua University. I also co-lead the quantum computing activity of the Italian National Center for HPC, Big Data and Quantum Computing, a large effort that has been funded by the European Recovery Fund in Italy, and I am a member of the executive board of PASQuants 2. And my activity there in PASQuants 2 in general are theoretical support to the development of quantum simulator on different platforms. So we work in close collaborations with experimental groups and with other theoretical groups exploring potential application on one side of quantum simulators, following closely the hardware development, and on the other side we support the development of very specific tasks that are needed to be developed to improve the performances of such tools. In general, one of our main tools are tensor network methods, which are very powerful classical methods for simulating quantum systems. So what we are able to do is to benchmark, predict, and also in some cases to perform digital twins of these wonderful, very complex machines that are quantum simulators and quantum computers that are being built now in all the labs belonging to PASQuants 2. The main goal of PASQuants 2 is to reach a quantum simulator of about 10,000 qubits by the end of this decade. So now we are in, let's say, almost in the middle of the first half of the FPA, and I would say that the status is great. So we have already achieved a lot of intermediate steps and results. We have been having very nice preliminary results from many different partners, pursuing all the directions that we have to develop and achieve to reach this main goal. So just to name some highlights that I like and that really give the idea of the development that we are achieving, is that we have already increased by one order of magnitude the number of atoms, for example, in Rydberg platforms that can be trapped. So now we are at the order of 1,000 atoms, and there have been very nice experiments that showed how it has improved our ability to prepare the system to manipulate them, and this is of course a necessary step towards the final goal. We are still not yet there, but we have many years to go, and we are very confident that the necessary condition to have at least 10,000 atoms already kept and stored in our systems will be achieved. On a parallel route, of course, we don't only need to have atoms, but we also have to be able to manipulate them and to extract useful information from them. So another very nice result that has been demonstrated by one partner is the ability of measuring complex quantities. So until now we were able to measure local quantities of each single qubits. Now it has been shown that in cold atoms in optical lattices we are now able also to measure directly currents and other important quantities that eventually will lead to the extraction of information, which is the relevant goal eventually of this quantum simulation. On the application part also we have been very, very active in, for example, enlarging the end user community. So we had many new industries that have been approaching us, have been participating to our periodic industry meetings, which are meetings specifically devoted to make industry and academy speak so that we can have the best, achieve the best from what we have now available. So the goal there is to explore potential application of current quantum simulators and of course of future in perspectives, and there we have seen, as I said, a growing interest by many different industries. Just to name a few, we have Thales, Alenia Space, which joined our community. We had the BASF that joined our community, and many others. So for each of these new industries, we are exploring new applications, and in some cases we have already some concrete proposals, concrete emulations and simulation of problems of industry relevance. I'm also very proud of an unexpected result that came out from our work in Padova, which is related to the factorization problem. So as I said, we have been developing powerful classical numerical methods to benchmark and support the development of quantum systems, and doing that we have been attacking very hard optimization problems. And what came out from a recent work is that actually we have attacked the factorization problem, the famous factorization that Shor's algorithm allows to solve in polynomial time if we had a quantum computer. Well, we have opened up a new route that can be ported on quantum simulator directly, and even more exciting, we have shown that with our classical methods, factorization might actually be polynomial as well. So we are of course, this is the beginning of a long story. We don't have the complete definitive result, but until now what we have seen is that factorization appears to be compatible with a polynomial scaling for classical computation, which it's a very nice and interesting result from a theoretical point of view. I'm also a member of a core group of a quantum coordination board of a quantum flagship, and this is a board that allows us, which is very important, and allows us to coordinate all the activity among all the different European projects funded by the quantum flagship and beyond, also by means of other programs. And this is a very important instrument that we have, and this is a fundamental tool that allows us to structure our research, coordinate, integrate, and find synergies between different projects funded under different programs, and to shape our request for the years to come. So this is, and then of course also with not only with that we make synergies and coordinate with other actions which are as important as the purely research one, as PASQUANS2, for example, but all the programs regarding to education, or as I said, with industries or with infrastructures, and so which the whole ecosystem has to be put forward and developed in a synergetic way, also because the challenge that we have ahead of us is so immense that only a coordinated effort of many different players can make it eventually to create a leading quantum ecosystem in Europe that can compete in the world landscape for the years to come. It also became very clear in the recent years that the quest for quantum advantage coming from either quantum computers and quantum simulators might really lie where we are working in, so in quantum simulation. A very interesting plenary talk here at EQTC 2024 by Professor Ignacio Sirac, which was explaining that there are very strong theoretical arguments which tends to converge to the fact that most probably the real power of quantum computer and quantum simulators will be exploited in analog or digital quantum simulation. So exactly at the core of PASQ2 activities. And that's why we are very excited to pursue this kind of research as a consortium. So I'm very excited about the next development now. So with the European Recovery Fund, we have seen a lot of national initiatives related to quantum that have been started. So we have a Munich Quantum Valley in Germany, we have Quantum Spain, we have in Italy a National Center for HPC, Big Data and Quantum Computing. And all these initiatives now will have, of course, to continue on in the next decade. We have been very happy about the fact that all the member states have signed the Quantum Pact, which is a political statement which recognizes the importance of quantum technologies for the future. So we are very happy and eager to contribute to shaping the landscape of European landscape for quantum technologies for the next decade to come.